All right, good morning, guys. We're going to have about 20 or so minutes to review, and then you guys will take your quiz the second half of class. Okay, so let's, guys can get out a sheet of paper. We can run through a couple of problems. All right, so we start off looking at this problem and asking ourselves, can we do any rearranging? Can we move any terms around? And we look at the denominator and there's too much, right? There's too much going on. If we try to bring it up, it's going to be raised to the -1, and we can't really distribute it through that 3e to the 4x. So we want to now consider u substitution. What could be a u value that will allow us to move towards one of these integral rules here? So maybe I can list out some options here. Maybe it's the 4x. Maybe it's e to the 4x. Maybe it's 3e to the 4x. Maybe it's -2e to the 4x. Maybe it's the entire denominator. So only one of these is going to help us resolve all the x's and bring us to one of these restrictive integral rules.
So it would be the whole denominator?
Yeah, I think that whole denominator is going to be the one that's going to have the best chance of getting all the x to go away and to match one of our rules. So the 4x and e to the 4x, these are a little bit too small. If you just let the exponent, yes, it would be perfect if it was just 3e to the 4x, then that 4x would be perfect, but there's too much going on. Then you're left with e to the u and then over 5 minus 2e to the u, and right, it's not going to match one of these rules, right? So if you went down the wrong path, I'm hoping that you'll be able to catch yourself, because you're going to look at the rules and you realize, wait, there's something right, I'm not able to get it to look like my rule. So if it doesn't match one of my rules, I got to scrap my u value and pick another one, preferably a larger portion if you're not able to get your rules to match. So e to the 4x, yeah, still a little bit too small. Now, if you pick the denominator, -2e to the 4x, that's a little better. But then you're left with something over 5 minus u. And we don't have a rule that can handle a 5 minus u in the denominator. So we have 1 over u, but that's all we have. If you have 1 over 1 plus u or 1 over 3 plus u, that's not the same thing. We don't have a rule then. So if we let the entire denominator be the u value, we should be able to make it all the way down to this 1 over u rule. Okay. All right, then what's our derivative then? Du dx. Here's
-8e to the 4x.
Yeah, so the rule for e to the u is simply just the original function times the exponent's derivative. The 5 goes away, but the -2 just kind of hangs in front of the as a coefficient. Okay, cross multiply. Okay, we make our substitutions here. Okay, e to the 4x drops out. We can push out that negative 3 over 8. And now we're left with a rule that matches perfectly natural log. And then replace the u back in terms of x. Okay, questions with one? Okay, here's number 2. Integral of 3x over x minus 1. Can we move things around and just, yeah, so denominator, we can quickly tell, right? If I'm adding a couple of terms in the denominator, I'm already out of that first option. So second option, u substitution. Okay, I think u substitution could work, but we got to go through a little bit of change of variable, right? So if we let u value be x minus 1, I think we can get it to work. So that's one option. What's another option that's available? Yeah, long division or synthetic division. I think this fits that criteria, right? Denominator has multiple terms, which is forcing us out of the power rule expansion option. But the denominator is a first degree, and the numerator is not, it's higher than or more than a denominator degree. So as long as the numerator degree kind of holds that degree as the same as a denominator, it is going to be a candidate for long division or synthetic division. And also, we have an expression that is basically a rational expression. So there's no like cosine or natural log or any trig function involved, right? It has to be a nice, clean, rational expression for us to even consider a long division or synthetic division. But yeah, let's explore synthetic division, because I think you know, it's going to be a shortened version of a synthetic division, but it still works. So we always pick the opposite value of what we see here. So basically, you're setting that expression equal to 0 and solving for x. So x equals 1. Put that number outside your half box. And now we're going to put coefficients of the degrees that are represented in the expression. So we start off with the 3. And we're going to keep going until we reach the what? So there's a linear, but we're going to keep going till we reach the constant. Yeah, so we're going to have a placeholder for 0 for the constant, even though it doesn't skip any degrees. It's nice to know where it ends. And if we know where it ends, then if we need it, we can kind of have that as a marker for knowing when to stop. Okay, any questions so far? All right, so we drop the 3 below the line, multiply, add, and that's where we stop. We started off with x to the first degree, so by the time we go through synthetic, what's going to happen? It's going to drop by 1, right? So this is now going to be a what? Constant. If that's a constant, then this must be a remainder. Yeah. So we have two. The nice thing about this is we have two separated terms. We can treat each like individual problems. They're not connected to each other. So this is power rule. This is an easy u substitution natural log rule. If you want to go through the whole u assignment, that's perfectly fine. But you could also jump directly to the conclusion, and I'll be okay with that. In fact, you can save some time if you do that. So this is basically just going to be a natural log. So when everything is said and done, we have 3x plus 3 natural log absolute value of x minus 1 plus c. So all this step in the middle is just to show how it matches up with the natural log rule, because we could go a little further here, pull that 3 out to kind of match it perfectly here. But we can save time if you can jump from this step directly to this step. Right? If you can make that jump, you can save a little bit of time. But only if you're comfortable with that. If not, then go through your use substitution steps. Okay, question with 2. All right, this is number 3 here. So what do you notice?
Bounds.
Bounds, which means that we got to deal with it, but not until the end, right? We don't touch it till the end. So I'm going to rewrite the problem without the bounds so I can focus my attention on my task at hand. Okay, what else do you notice?
The numerator happens.
Okay, what about the denominator? Just one term. Okay, so if there's only one term in the denominator, we at least want to explore the possibility of maybe merging, bringing it up to the top. Is this something that we can pursue in terms of putting things together? Actually, you know what? Usually, we combine things if everything in terms of x's. But notice that these are both under the same family of functions. So we can actually put things together. Now, if this is like cosine or natural log or anything else, then we're kind of, out of luck there. Or even if the numerator was like x squared minus 1, but there's e to the 2x. But everything kind of falls under the same family here. So we can actually move it up, and actually we can clean this up a little bit. So 2 ways they can do this. You can either move it up and get a fraction to distribute, or not fraction, parentheses to distribute. Or I find it sometimes, for some of you, maybe it's more helpful just to think of it as splitting into individual fractions. That way you're always remembering that your numerator is impacted by the denominator for every term. Okay, the same result there. So whether I bring it up and distribute or split up into individual fractions, what's the cleanup version of this expression? This becomes what? 1. And is there a cleaner way to write this second expression? So I'm always looking to see if it's going to match my rule. So if I want to get that e to the 2x, where should it be?
E to the negative 2x?
Yeah. So I'm looking ahead and I'm looking to see, well, looks like this could be a good fit, but only if it's in the numerator. So I'm going to push that up. Now, if you distribute it this way, maybe it would have already been showing that. So, but we want to bring that up. So look at where we started. Look at what we have now. This is a little cleaner, right? They mean the same thing, but we can now treat them like separate problems. So I'm going to just visually create them as separate problems. So this I can just use power rule. This one I can use what? Just a little bit of a little bit of u substitution, right? Now, can you look ahead? What's going to happen with that negative 2x? Any idea? What's going to come out of that negative 2x? Close. Yeah, negative 1/2. Negative 1/2. And until, if you're comfortable, you can make that jump. I'm going to show the whole u substitution step, but down the road, we can really save time if we just understand that we're really just dealing with chain rule, but the opposite direction, right? So it's basically, it's not times u prime, it's going to be times the reciprocal of u prime, because we're undoing that chain rule. So, but I'll go through the whole process and kind of show you, kind of convince you of that. But you only want to do that for kind of relatively simple linear u values. Anything that's more complex, you really want to spend the time to make sure that you have everything in place. But I think the easier ones, you can speed up that process. So let's say our u value is negative 2x. So do you guys see that? This negative 2x is producing a negative 1/2. It's always going to happen. So if you can spot that pattern, we can save some time. But we get negative 1/2 e to the u. I'm just going to go ahead and replace the u back in terms of x. So there's my antiderivative for my second term. The 1 will become an x. So I'm just going to do method 2 in this case, because having this is already in terms of x. So just be cleaner that way. Now careful, there's a minus here and there's also a negative here. So I'm going to go ahead and move that 2x back down. Yeah, you can. Yeah, you can definitely make that jump. I just want to show that we got to resolve two negatives. But yeah, you can make that a plus. Perfectly fine. And then we can use our original bounds, right? I represented my antiderivative in terms of x. So my original bounds are good to go. Okay. Upper bound always gets evaluated first. Okay. Minus, then we repeat the process for the lower bound. And if you leave your answer like this, oops, second, not first. If you leave your answer like this, I'm okay with it. This is fine. You don't have to clean up your answer. Now, if you leave your answer like this, then we haven't gone far enough. I want to see that you can evaluate your bounds, but this is fine. If you want to go further, you can, but on the AP exam, if it's non-calculator, they would accept that answer. So yeah, I'll just leave it in that form.
Hey, Mr. Yang, can we do a
Yes.
synthetic division problem, you think?
I'm sorry?
You think we could do a synthetic division problem?
Yeah, we did a short one with number 2, but you want a longer one?
Yeah, if we can.
Okay, all right, I'll do it.
Thanks.
Okay, so this one is a good candidate for synthetic, right? Too many terms, we can't move up, we can't do power rule, use substitution doesn't work. So pull the opposite sign. And tell me the numbers that go in this top row here.
4,
Mhm.
2, 0, 7.
Okay, close. The second one is going to be a -2, right?
Negative
Okay,
2.
-2. And then why do you say 0?
Because it's between x to the squared and then x to the 0.
Right. Every degree needs to be represented from where we start until the constant. So we have a representative for x cubed. We have a representative for x squared. We have no representative for x. Oh, so we need to have a placeholder for it. So we'll put a 0 in for that spot, and finally the constant. Okay, bring down the 4, multiply. Sorry, I didn't mean to be such a large value here. We started with x cubed, so where are we going to start with this, with our new quotient? X squared. And every term is going to fall by 1 degree. X squared, followed by x, followed by the constant, and then finally remainder. Okay, is that what you guys got? Okay. So we should have an easier time now with each of these terms. They're nice and separated. Power rule for the first 3 terms, and then a natural log for that last term there. All right, your quiz is about to be released.